Right. So Ramsey's theorem says that whenever you color the edges of the graph, you can find the complete subgraphs whose edges are monochromatic. Now, what if we color the vector space, or more generally, I mean, it's not more general, but affine space. So let me first describe what we mean. So F is finite field. The reason why we worked on finite field is because the number of subspaces is finite then. And we say X in F of n is a T space of F of n if it is an affine subspace of dimension T. All right. So for instance, zero space are just a single point. So let me say in other words, T space is a translate of a linear subspace of dimension T. So when you have a subspace W, vector subspace or linear subspace W and A, then A plus W is an affine subspace of dimension T. So zero space is just a one point, and one space is same as a line, right? And two space is a plane, and now it's difficult to draw anything higher. Now here's a interesting looking theorem. Oh, by the way, let me define further notations. For this section only, I'm going to use this bracket notation to denote the set of all T spaces of phi. There are only finitely many such T spaces because field is finite. And here's the theorem. This is due to Graham and Lieb and Rothschild in 1972. And let's call the affine Ramsey theorem. For all K and R, there is n, let's say capital N, such that for all n bigger than or equal to capital N, any R coloring of the T subspaces of F of n induces a K subspace, K space. Yeah, I think I just call T space. K space W whose all T spaces have the same color. So this is similar to the Ramsey theorem of graphs. Instead of coloring edges, we are coloring subspaces. We color the lines or planes, right? So, and we are coloring all the lines by one of these R colors, and no matter how we color them, there will be a T space whose there will be a K space whose all T spaces have the same color. So in other words, if we use symbols, in other words, like if dimension of V is n bigger than capital N, and chi is a function from all T subspaces to R, then there is W in K, which is K space, such that this coloring function is constant on W choose K T. Okay. Right, so before proving this theorem, let me show you the easy cases first. So as a lemma, let's say, so it's true when T is 0. So what does that mean? We are coloring 0 spaces. So 0 spaces are points, right? So for all RT, for all no T, or for R and K, there is N such that for all N bigger than N, any R coloring of Fn induces a monochromatic K space. Why? And this is a simple application of Hell's-Drude theorem. Right. Take M to be the Hell's-Drude number of the size of field to the nth power, kth power, and R, and capital N to be the M times K. Now, there's a natural bijection. Bijection from F to the N. Okay, so we assume N is equal to N, because if you have a bigger vector space, I'm gonna just take the subspace, right? So I can assume that N is equal to N. Well, I don't actually need, alright, it doesn't matter, yeah. So natural bijection from F to the N to F to the, F to the K to the M, right? Just look at the, let's say this is F to the N, right? These are coordinates, and I'm representing a vector as this boxes. Now I cut for every length K, I cut, and then now I think of it as has an element in f to the k to the m, right? Where each of this is one alphabet. So the number of possibilities is f to the k, and then there are m of them. And so by Hertz-Duet theorem, since we have this many possible alphabets for each coordinate and we have this many colors, there is a combinatorial line described by a root tau in like f to the k union star to the m's power. Now, star, what is a star? Star is represented by this length k, but this star, you can think of it as like x1, x2, xk, where x1, x2, xk are the vectors in f and points in f, right? Now, the points in this line correspond to something like a plus something like a plus b1 x1 and b2 x2 and bk xk, right? Where b1 is the number of times that you have a star. Oh no, actually, am I doing right? Yeah. Let me let me give you an example. So for instance, I have 1, 3, 2, and this is star, so the x1, x2, x3, and 4, 5, 0, right? And I can put any x1 to 3 by any value, and all of them have the same color because that's combinatorial line, and this line correspond to, yeah, I mean they correspond to, right? So what we have, so when you don't have a star, then it's A, and when you do have star, then that's W, where W is spanned by and W is just oops. Yeah, so it's like oh, I see. All right, so so I can write it. So the point in this combinatorial line is like A plus x1 b1 x2 b2 xk bk, where bi's are the 0, 1 vector and right representing the location of xi's, and xi will be the just any value here. So this is affine k space, right? Yeah. So so this shows you that when t is 0, then it's trivial. Now let me show you another corollary, simple corollary of Herzog theorem, which we will use later. So let's say F is finite field. Oh, by the way, maybe I should mention that inside theorem, yeah, so F is finite. Inside the lemma, I should say F is finite. The function depends on the field, right? So F is finite field, and let M be the Herzog number of finite size of finite field to U plus 1 and C. So C is the number of colors. Let chi be the C coloring of the ordered U plus 1 tuples. U1, U2, no, X1, X0, X1 up to XU, where Xi is in F to the M. So it's a description of U space, right? I mean, if they are independent, they're generally, I mean, if these U plus 1 points are not degenerate, then they will span a U space. Then there exist parallel affine lines L0, L1 up to LU in F to the M, such that L0 times L1 times L U is monochromatic. So that's the another consequence of Herzog theorem, and here's a proof. Let us regard this U plus 1 tuples X0, X1, XU, where each Xi is F to the M, as a M by U plus 1 matrix. So here you have U plus 1 column, so you have M rows, right? So it's right. Let's regard that. Now I'm gonna look at the rows. Now consider rows, right? And number of rows is big. And number of possible distinct rows is at most, of course, it's at most F to the U plus 1, right? So since M is this Herzog number of the F to the U plus 1 C, we deduce that there is a combinatorial line. L described by a row, a column vector, tau in let's say F to the U plus 1 I mean, it's described by some column vector in union star to the m's power. But what is this combinatorial line? So some row becomes star, some rows is fixed. So that means there are a few star rows where all possible values can be added, but all these rows are identical and all other rows are fixed. So what does that mean? That means if I look at this matrix in terms of column vectors, right? What do we get? And by the way, what do we mean by combinatorial line? Well, I mean, what is the coloring? So I have a coloring for all ordered U+1 tuple. So we have coloring of this matrix. Yeah, so this matrix, for each matrix you have a C colors. I mean, one of the C colors. And then we have a set of matrices, which is described by this root, the combinatorial line. And this set of matrices all have the same color. And what are these set of matrices? Well, you have x1, x1, x1 here, and x2, x2, x2 here, etc. Until like, okay, let's start with 0, 0, 1, 1. Yeah. xu, xu, xu. And no matter how I put xi from f, all of them will have the same color. So if I look at one column, then some rows are xi, xi, xi. Right? So if I look at the ith column, so Li is the set of points a plus bxi, ai plus bxi, pi, okay, xi, pi, where xi is some entries in F, and ai is the column vector representing columns with no stars, and pi is the column vector 1 vector where when xi is there, then it's pi, right? And then this is a combinatorial, this is part of the I mean, this represents the ith column, and this is a line, this is an affine line, right? It's a one space. And you notice that then L1, L0 times L1 times LU is monochromatic. This means that you pick one column from L0, you pick one column from L1, one column from L2, up to one column from LU. All of these columns, when you combine them together, you have a matrix, which is combinatorial line. And which is in this combinatorial line, which is monochromatic. All right. Okay. All right. Now we are ready to start the main proof of the affine Ramsey theorem. we're gonna introduce a few terms. So suppose I have a coloring of T spaces. The V is this n-dimensional space. Coloring of T spaces with R colors, and let B be a U+1 space of V, and P be a surjective projection. Just by ignoring the last coordinate. So you have a kind of like you have a mapping from U+1 space to U space, ignoring one dimensions. Then for each T space, T in BT, we say two things. T is transversal with respect to P if dimension of PT is still T. So when you go down by projection, you still keep the dimension. So you didn't lose the dimension, then we say it's transversal. And otherwise, T is vertical. So the space loses one dimension, then it loses, right? So like what it could be, here's a one space, but if I project over here, then it becomes a point. So you lose one dimension, then it is called vertical. Then in this case, if vertical, that means dimension of the image is T-1, right? Because you start with the dimension T space, and you take a projection, then you have dimension T-1. And when you take inverse of the image, well, it contains T obviously, but it doesn't contain more because you can only increase the dimension by 1. And this projection only lose one dimension, so you can never have a dimension 2 by projecting it. You can never gain 2 dimensions by taking inverse. So this is what we know. So in other words, T defines some vertical directions, right? So if it's vertical, then you have one directions. Anyway, we say B, the U+1 space B is special with respect to chi and P if the color of two spaces are equal whenever their images is equal. Well, whenever their images for all transversals T1 and T2 in BT, right? So whenever I look at the T space inside B, if they are transversal, then their images, the projection, the image in the projection determines the color. Then it's called spatial. Now here's a lemma that for all TUR there exists M, which is MTUR, such that for any R coloring chi of the T spaces of F to the U plus M R and the projection P from F to the U plus M to F to the U by taking the first U coordinates, there exists a special U plus 1 space B with respect to chi and P. Right. So this means that if I have a big dimension, then I can find the space U plus 1 space which is special. So the color of the T spaces inside this U plus 1 space is completely determined by their images, projection, their images. Like, I mean, yeah. So colors of transversals inside this U plus 1 space B is determined by the images. Right. So how do we prove it? Let V be with the number of T spaces in a U space. Since F is fixed, this is fixed and finite. Since F is finite, this is finite. I should say F is finite. Since F is finite, V is finite. Okay. Now we take M to be the Hessian number of F to the U plus 1 and R to the V. And let us fix coloring on R coloring chi from the T spaces to R. Now I'm gonna define vectors E0, E1, E2, EU be vectors in FU so that EI is a vector, one of the vectors in the standard base. Right? So they become a basis, right? So that E1, E2, EU is the standard basis. Now let AI be the inverse of this EI for I from 0 to U. Then AI is a copy of F of M, right? Because we are fixing the first U coordinate and the remaining is anything. So it's a copy of F of M, which you can obtain by moving at some place. Now let x0, x1, xu be a u plus 1 tuple of vectors in f of m. Now let yi be the ei and xi. So what that means is this is a vector in ai. I'm attaching ei part and an xi part. Then that's yi. So yi is a vector in ai, and whose last m coordinates, so the first u coordinates are just having is same as ei, and the last m coordinates are same as xi. Now then y 0, y1, y2, yu generate a unique u space x in f to the m. So what does this mean? In an affine geometry, a set of vectors generate something, right? In affine geometry, so x is going to be like a set of ci from 0 to u, where the sum of the ci has to be equal to 1. That's a subspace, and it's a u space. Now remember we had this projection P. Then let's look at the projection restricted on x. And this is still surjective. Right? Because it automatically contains E0, E1, E2 up to EU. So this is surjective mapping. But x has dimension what? X has dimension u. So it's actually injective too. Right? So actually we can say it's bijective. Right? Dimension of x is equal to u, and this is equal to dimension of f of u. So it's bijective. This means that x is transposer. Right? So the p of x, well, I mean, I guess I could say that another way of saying it is dimension of x is equal, yeah, I mean, I already have it. Yeah, so x is transposer. It didn't lose any dimension. Oh, when I defined transposer, I should have said correctly. So dimension of pt is equal to dimension of t. Okay, here's what I'm fixing over here. All right. So x is transposer. Now I'm going to take all possible subspaces of T. Oh, FU. TV be the list of all T spaces of FU in some preassigned ordering. Now we define a coloring. Of fm to u plus 1 by, right? So chi prime x0, x1 x0. So I'm as the tuple of the colors. So this is like chi of t1 and chi of t2 and chi of tv prime, where ti prime is the unique t space in X such that p of ti prime is equal to ti. It's because it's bijection, there's an inverse, right? So in other words, ti prime is the p inverse of ti. So in this coloring, two u plus 1 tuples have the same color. Then their corresponding U spaces have the same color. Okay. No, the T spaces. All right. Now, by the previous lemma, using the Hertz-Drude theorem, there exists yeah, so how big do I need? Let's look at this corollary, right? I have this many colors C. So there exists affine lines L0 and L1 LU parallel to each other so that this is monochromatic in chi prime, and L0 L1 when I combine, when I take all these lines and then this generate a U plus 1 space B. Now, because these are parallel lines and there are U plus 1 of them, so when you combine them, you can generate U plus 1 space. All right. Now, we claim that B is special with respect to chi and P. So in order to say why it's special, I need to say that the transversal of the color determined by its projections. So let T be a transversal, P transversal, then there is J in one of these V such that when I take a projections, then it becomes Tj, because I had a list of all T subspaces, so one of them must be equal to this. Now we can extend T to a transversal U space. Right, just by linear algebra, we have transversal T space. Now I'm extending it, finding a direction to extend T, which also increases the dimension in the projection. And I can do it until I hit the dimension U. So this is guaranteed by linear algebra. So I have a transversal U space X inside B. Right? Simply not to choose the wrong direction. Like if you, as long as you choose good direction in the projection, you're gonna increase the direction. Well, I mean, another way of saying it is like increase Tj by a direction whose projection will also increase the dimension, and you can do it. All right. So we find the U space X, which is transversal and which contains X. And Px is everything. Since AI is P inverse of the EI, there exists YI in X intersection AI for each I. Then X is generated by Y0, Y1, and YU, and T is contained in X, right? Then chi of T, what is the color? Is the J's coordinate of chi prime of X0, X1, X2, and XU, where YI is equal to EI and XI. Remember? As chi prime is constant. Right? Chi prime is constant by the Hertzsprung theorem, right? And no matter how I choose like X1 here, X0 here, X1 here, XU there, you have the same color. Okay? Because it's in B. So chi prime is constant. That means the J's coordinate chi T is determined by J, right? And this choice of J is fixed. So J is determined by projection of T. Right? So that just means that this becomes special. All right. Now let's prove the theorem. We're going to prove the following form. Which is stronger than the affine Ramsey theorem. I mean, it's not exactly stronger, but it's better. It becomes easier with induction. So for all T, R, and K1, K2, KR, there exists N. Which is as a function N, let's say T, K1, K2, KR, satisfying the following. Let V be on N space and chi be the coloring and R coloring of T spaces of V. Then there exists W, which is a Ki subspace of V for some I such that chi T is I for all T in the T subspace of W. So this is a more refined version than the previous statement. Here we are aiming to get a like K1 dimension, K1 space, monochromatic K1 space of color 1, or K2 space of color 2, or K3 space of color 3. By color 3, I mean all T subspaces, all T spaces have color 3. So instead of saying you have a what is it, K space of whose all T subspaces have color, I mean monochromatic, all T spaces have the same color, we are describing the exact different dimension. So that's the claim. So this is obviously stronger than the I mean this obviously implies what we want, right? So what we want is here. By the way, this is a proof by Spencer. So initial proof is more complicated, right? So in this case, instead for this K, we can put K1, K2, KR to be equal to K, then what you get is this form. All right. Now let's see how to. So we gonna do the double induction, but so among all count examples, choose one with a minimum T, and subject to this, choose sum of Ki minimum. Okay. If T is 0, then what does that mean? That means we are looking at the 0 space. Then it's already true. then we are done. Why? Because we did this, right? We already treated the case when t is 0. We can use Hair's-Drude theorem and take a ki to be k to be maximum of ki, and then from lemma here we can find the monochromatic case space. So from the lemma, using the Hair's-Drude. So we may assume t is bigger than 0. Now let me tell you the setup. Let S be the maximum of that. So everything else is same except ki you subtract 1. So that's S, and U is n of t minus 1. And so what is U? This is, we already have a function for affine Ramsey theorem. So this is that function, and I need a function for this. Well, what lemma? Oh yeah. So let me write this way. So n t minus 1 s s s s, and these you have r of them, and m is mt of the u semicolon r. So this is from the previous lemma about the existence of special subspace, and then we will define n as u plus m. Okay, that's the constructions. Now we will show that this n satisfies the claim. Right? So let's say chi f is equal to f of n, and let chi be a coloring. So n is u plus m, so u plus m, and I'm coloring t spaces by r colors. And let P be the projection from u plus m space to f of u. The projection taking the first u coordinate. Alright, by the definition of m, in the previous lemma, remember, so what was the previous lemma? It's about special subspaces. Yeah, here it is. Previous lemma, there exists a special u plus 1 space b with respect to chi and p. All right. So in this special subspace, the color of T space, transversal T space, depends on the image in the projection. All right. Now, let chi prime be a coloring of fu T minus 1 space of T minus 1 spaces of fu such that chi prime of T is chi of P inverse T. In other words, what does this mean? So we give a coloring right? I mean, the thing is, P is a projection from U plus M, Fu plus M to U, right? And B, oh yeah, so right. Okay, let me say this way. P restrict to B inverse T. So P, so we are restricting this projection function to B, and then when I take inverse with respect to this P, then it becomes, so this is subset of B, and B has demands on U plus 1, and T has demands on U, and T has demands on T minus 1, right? So the projection of P, projection of B has demands on of projection of B is U, right? So that means we lost one dimension. So when I take inverse, we will gain one dimension. So that means dimension of P inverse T is gonna be T, right? We gain one. Then each subspace, each T space has color. So in other words, chi prime gives an R coloring to T minus 1 spaces of Fu from a vertical T space, from a color of a vertical T space, giving, yeah, when you have a vertical T space, after the projection it becomes a T minus 1 space. So that's the coloring. So it's, I mean, remember the proof for hypergraph Ramsey? We also had a step that reduces this problem to a smaller instance where the edges of the hypergraph has a smaller cardinality. So this is similar situations. Okay. By the induction hypothesis, or by the assumption, we assume that t is minimum, right? There is a monochromatic, okay, I mean, let's say there is x, which is S-dimensional, no, S space, such that well, that is monochromatic, such that all t minus 1 spaces of x have the same color. Same color. And by symmetry, say 1 under chi prime. All right. So we found, so inside, so here we have a big space, u plus m space. Here's u, here's m. Then inside here I found S space. Right? So that all t minus 1 subspaces have the same color. And S is bigger than n. Oh, why, by the way? Oh, no, it's okay. Now, S is bigger than nt minus 1. No, nt, k1 minus 1, and k2, k3, kr. So this implies that by the assumption, there exists W1 in X. I mean W1, which is a subspace such that either dimension of W1 is K1 minus 1, so it's, and all T spaces of W1 have color 1, or dimension of W1 is Ki, and all T spaces of W1 have color I. If we have 2, then we are done, because we already found 1. Again, you can think of this as an analog of the graph Ramsey theorem or hypergraph Ramsey theorem. I mean Ramsey theorem for such system. And so if it's the second case, then we are already done. So we may assume that we have first case. Right. Now take W as the inverse of W1. All right. Then dimension of W, because we are increasing dimension by 1, so this is going to be K1. And W is a vertical K1 space of B. And if T is a T space of W, if T is transversal, then chi T is T is transversal, then PT is same as T. I mean, we didn't decrease the dimension. Right? So oh, I didn't define the, did I define the color? Yeah. Yeah, I forgot to mention the coloring. What is this color? This B is a special, B is a special, right? So that means all transversals have the same, the colors of transversals are determined by its images. And that's the coloring here. So then the color, then by 1, the color of T is 1. If T is vertical, then it is a vertical T space. If T is vertical, that means, remember, chi prime of PT, when you take a projection, was 1. So that means chi of T is 1. So all T spaces of W have the same color. Okay? So that's the proof. So this proof was due to Joel Spencer in 19, let me see, when was it? 79. Now here's an interesting corollary. And the thing is, we can also deduce this vector space Ramsey theorem. So let me first state it and then explain why this follows easily. So for any R, T, and K, there exists N such that for any R coloring of the T-dimensional subspaces, so here it's vector spaces. So subspaces are really linear subspaces, not affine subspaces of an n-dimensional vector space V over or fixed finite field there exists. So the function n depends on the size of field. There exists a k-dimensional vector space. Well, k-dimensional linear subspaces W whose all t-dimensional subspaces have the same color. Why is this true? The thing is, if let's say I have a coloring of t-dimensional subspaces, then what do? I'm gonna color t-1 space. Right, so for instance, let me think of this case. So if I have a line, so when t is 1, this is a one-dimensional subspace, right? But now we map it into a t-1 space. Why? I mean, just take the one vector in here, and that's the, I mean, all right. Right. So what's the correspondence if I have a if I have a plus b w right, I mean, what is the easiest way? Okay, so here's the origin 0, right? Take some hyperplane not going through 0, and then take intersection with this hyperplane. But when you choose this hyperplane, I want to choose it so that it doesn't intersect. It doesn't. I mean, it's not degenerate with respect to the others. I mean, what I mean is it's not parallel to any of the existing ones. All right. And then one-dimensional subspace. Oops. One-dimensional subspace become a point, and two-dimensional subspace become a line, right? So there's one-to-one correspondence, except one. Yeah, so that's what it is. Right. So we apply affine Ramsey theorem for t-1 case, and then we do the same thing. All right, that's it.